Hi, I'm Katie Early. Welcome to Part 2 of the Number Sense module for grades 3 through 5. You will be hearing my voice and that of my three colleagues, Danielle Reynolds, Brian Lindeman, and Michelle Sanchez. We are excited to share this part of the module with you and hope you find it beneficial to the students you serve. Here are the topics we will be discussing in Part 2 of the module. These are also included as links in the description below. What does it mean to be flexible with numbers? Please take 1 minute to jot down your thoughts. Let's now look at how the major focus areas for number sense at each grade level progress in the continuum from 3rd through 5th grade. In grades 3 through 5, students extend their flexibility with number as they understand the more advanced operations of multiplication and division and how these two operations are related. They use number lines as tools to solve multiplication and division problems involving larger and smaller numbers and apply number line strategies to make sense of operations with fractions and decimals. How do students in grades 3 through 5 extend flexibility with number? Students in these grades need ample opportunity to build connections, refine calculation strategies, and make use of patterns in mathematics. As they work with larger numbers and fractional quantities, they apply strategies and properties they have previously used. Grade 3 students use strategies to add and subtract numbers, estimate to approximate results, identify number patterns, illustrate strategies, play with numbers. Grade 4 students recognize whole numbers as the products of factors, identify and generate numerical patterns, make sense of decimal place values, model with fractions extensively, build fractions from unit fractions. Grade 5 students use concrete and representational tools for decimals and fractions, use strategies such as benchmark numbers, common numerators, and common denominators to compare fractions.
Number talks include problems such as these in true or false format. They challenge students' understanding of the equal sign as expressing a relationship between quantities rather than as an operation symbol. As students solve these problems, what understanding, properties, and reasoning can you identify that underlie these relational thinking questions?
What models and tools do students in grades 3 through 5 use as they develop understanding of multiplication and division? Students use a wide variety of physical tools and illustrate the problems they solve. Tools and models that have meaning to the students support the development of deep understanding and enable students to connect physical and numerical representations of mathematical situations. In grade 3, students model multiplication initially using objects and illustrations as addition of equal-sized groups, and later as arrays and areas of rectangles and as equal-sized jumps on a number line. In grade 4, students use strip diagrams, number lines, and drawings to make sense of multiplication situations, including multiplicative comparisons. They use models, estimation, decomposition, and place value concepts to multiply larger numbers, and they recognize the inverse relationships between multiplication and division. In grade 5, students use place value, properties of operations, and the inverse relationship between multiplication and division to find whole number quotients of whole numbers with up to 4-digit dividends and 2-digit divisors. While students develop efficient strategies for recording their thinking as they multiply in grades 3 and 4, the fluent use of a standard algorithm for multi-digit whole number multiplication is expected by the end of grade 5, according to the California Common Core state standards. How do students in grades 3 through 5 come to understand the operations of multiplication and division? A challenge for many students, and therefore for their teachers, is to connect physical and pictorial representations of problems with the more abstract, symbolic representations, often equations, that correspond to the concrete visualizations. Next, we will watch a video from Graham Fletcher, The Progression of Multiplication. As you watch, consider the following questions. When and how do young students begin work with multiplication? How do students make sense of the relationship between multiplication and division? How do students connect physical models with efficient numerical methods of multiplying? How do we support students in representing multiplication situations?
So, here's my attempt to explain the progression of multiplication. Well, most of us might think it starts in third grade, but in actuality, it starts in second grade, where students are expected to take a square or a rectangle and partition that square into no more than 5 rows or 5 columns. Here, the understanding of repeated addition is established. 5 plus 5 plus 5 plus 5 plus 5 is 25. Then, in third grade, students take that understanding they begin to develop in second grade and begin to construct arrays using square color tiles, or any manipulative for that matter. The important piece is once they've actually constructed that model, they draw a pictorial representation which matches their model. Here we have 4 rows of 6, or it could also be seen as 6 rows of 4, depending on how you turn the model. And the big piece here is that we don't push an understanding on students, we let students explain what their model represents. The big piece is that the context will explain the equation, not the teacher. Then we take that understanding and we come back to the biggest piece probably in third grade, which is that there's a relationship happening here. And that relationship is taking place between multiplication and division. Take this, for example. 12 divided by 4 is a number. 4 times what number is 12? Well, if we take 12 tiles and we put them in 4 rows until we run out, we actually see that we have 3 in each row. So there's a connection between multiplication and division, and arrays can be used for both. The context. Yep, let's go back to it. Here's a simple one. There were 3 packs of pencils. Each pack had 40 pencils. Well, at the beginning part of multiplication, students might do something like this, where they draw out 3 circles, and in each circle they put in 4 10 rods, so 40. Or they could actually go ahead and draw 40 little pencils. That's great. But the standards of mathematical practice, and in particular number 7, want us to be efficient. And one way to do that is we can begin to make use of structure. And when we do, we make sense of it. Here we begin to create an area model for multiplication, very much like an array, just on a bigger scale with larger numbers. So 3 times 40, we take it, build it out of 10 rods. We have 10 tens, which is 100, plus 20 is 120. Or it could also be seen as 12 tens. Really big understanding for students. Once students have established this, they should be diving into drawing pictorial models for what they're concrete. Again, we don't want them to be sitting there with manipulatives all the time. So we move them away and they begin to draw a pictorial representation for what their concrete model looks like. Then from there, we'll have them use numbers to represent their picture. All of the time, connections are being made. Then, eventually, after multiplying all of these ones and tens, students begin to collect and group numbers together. Now we're beginning to become efficient thinkers. The connections are being made all around because students are exploring. In 4th grade, students are expected to multiply 2-digit by 2-digit numbers. So what does this look like with a concrete model? Well, it kind of looks the same, really. So we have 23 across the top and 22 down the side. 10 times 10 is 100, and that's where those 100 plates come into play. Then, once students have gone ahead and actually built a model, They see that they have 4 hundreds, 10 tens, 6 ones, and they add that all together, 506. Then, just like we did with smaller numbers, we expect that students should draw a pictorial representation which matches their concrete model. We can see the 100 plates, the 10 rods, and the 6 ones. There they are. Altogether, 506. And just like before, we'll ask that students go ahead and start using tens and numbers to actually represent their model. So what you're probably thinking right now is this is not efficient. There's too many tens going on here, too many ones, and students are going to get confused. And you know what? You're absolutely right. And it's at this point where kids say, this sucks. We need to find a shortcut. So what do? They begin to group and collect their numbers just like they did before. So here we have the box method. But in reality, it's partial products. So let's not call it the box method anymore and start calling it by its real name. Then we take that partial product understanding and we begin to formalize it into some kind of standard algorithm. Yep, this is a standard algorithm. It's a series of repeated steps. And you can see where each of the numbers come from. Then we have the algorithm that we're all pretty much used to. But you see that 0? Now the connection is made and students know why we magically put that 0 there. But all this understanding happens at the end of 5th grade. Let's not rush them. There's so much happening here and so much to explore. Let's slow down a little bit.
You may have discovered other valuable insights as you watch the video. We invite you to discuss these with a colleague.
How do students in grades 3 to 5 come to understand the operations of multiplication and division? Next, we will watch the progression of division. As you watch, consider the following questions. What is the importance of context in making sense of division? How does the action of dividing differ depending on the meaning of the divisor in a story problem? How do students make use of the relationship between multiplication and division? At what grade are students expected to use the standard US algorithm for long division? Also reflect on the use of visual models and how students build connections between these models and written expressions, such as the partial quotients method.
Of all the things that students must learn by the time they leave elementary school, division might be one of the toughest. So here we look to tackle the progression of division, and it starts in 3rd grade. So take this for example, 12 divided by 4. Let's see what happens. Well, we have two completely different models. And what this says is that the context, the story of the problem, plays a large part in developing students' conceptual understanding. In one, we have 12 bears with 4 in each group, which gives us 3 groups, and 12 bears shared with 4 friends, which leaves us 3 with each group. One model, well, that's measurement or repeated subtraction. The other is fair share, which I think we're all pretty familiar with. In one example, we have the group is unknown, and in the other, the size of the group is unknown. As students begin to develop their understanding of division, they probably begin to really rely on this fair share model. But 54, that's going to take a long time using fair share. So we need to put students in a place where they begin to become more flexible and efficient thinkers. So they might begin, instead of doing 1 by 1, they might say, I'm going to take out 5 and put 5 in each group to start. Then, with their remaining pieces, they might put 2 in each group, and so on. So within each group of 6, they've placed a group of 5, a group of 2, and another group of 2. So when you take 54 and you divide it into 6 groups, you get 9 in each group. Now here students are making the connection between the concrete, the representation, and the abstract. And you know what? It all makes sense because students are building these pieces conceptually. As students begin to explore again in 3rd grade, they deal with quotients which are greater than 10. Here students might begin to explore the idea of division with base 10 blocks. So they'll start with 72, and instead of putting it into 3 groups, they'll put it into 3 rows. They'll start by placing 10 in each row, then 10 in each row, and then they have that 10, and in order to place it in each row, they need to decompose it, make a fair trade. So you can see that when we take 72 and we divide it into 3 rows, we have 24 in each row. And then we want to make that connection from the concrete with the base 10 blocks to the representation. And how do we record our representation in a written expression? And some students might begin to collectively group their tens, and that's where the 20 came from. The best part about this is that students are making a connection back to multiplication by using the distributive property, and they're seeing it visually. In 4th grade, yeah, that's right, all that understanding we just saw should have been happening in 3rd grade. But it might not be mastered. But in 4th grade, students will take 4-digit dividends and 1-digit divisors and begin to extend their understanding of division. But one thing has to be taking place, and that's continually making the connection between models and representations and written expressions. Here we'll take 144 and divide it into 9 groups, 1 into each group, and so on and so on and so on. Again, that fair share model. But what does that model look like as a written expression? Well, here the students repeatedly removing groups of 9 from the 144. Now, is this efficient? No, not at all. But it's really important that students work through this step and they realize what efficient and non-efficient thinking looks like. So after students do the example of 144 divided by 9, we might throw them in a place with this number where the dividend is 3,672. Well, they start removing groups of 9 and immediately they say, oh wow, I'm going to be here forever. This is going to take the longest time. Can I take out a group of 100? Sure you can. You can take out whatever groups you want. So they can take out a group of 100, a group of 200, and then another group of 109s, and then a group of 6 9s. Students have to make sense of the mathematics, and we can't tell them what to do. So here, they're removing their partial quotients. So from the expression, they go ahead and create an area model. And what's beautiful about this area model is that it connects back to multiplication, except it's the area model for partial quotients. Then, as students begin to dive into 5th grade, they extend this understanding that they've built conceptually from 3rd and 4th grade, only this time they deal with 4-digit dividends and 2-digit divisors. The big piece here is that students deal with numbers and equations where they'll only have whole number quotients. All that means is that the decimal shouldn't be in the answer, but it can be in the dividend and we can have a decimal in the divisor. So here we make that connection again between the representation and the expression. And we write our partial quotients off to the side, just helps us keep track. So students might not know all their multiplication facts, but they do know 3 or 4. So here's their products of 32. Every student will know these. Let them start there. Now, decimals. What about decimals? Well, this same understanding of partial quotients and area model can be applied to decimals. Here we have 1 and 24 hundredths, and we're continually removing groups of 4 hundredths. Connections are being made, and it's a progression, which makes it much easier for students to move between whole numbers to decimals and from decimals back to whole numbers. There's just an example. Instead of using 3/10, a student might think flexibly and use 25/400ths. Now, in sixth grade, students encounter the term standard algorithm. And all that really means is a series of repeated steps. So, if students have used this same understanding of partial quotients from third grade, this is a standard algorithm. So, let's see what a student might do. Well, in 8,425, I want to remove 200 groups of 32, and then 60 groups of 32, and 3 groups of 32. Let's look what it looks like with the standard algorithm. Well, 32 doesn't go into 8, but 32 goes into. What does that mean? And here we have the traditional algorithm, which many of us are familiar with. But you see how there is a connection between the two. Which one has understanding? So there's lots of things taking place, all the way up from third grade to sixth grade. Let's not rush it. Remember that the turtle won the race.
You may have discovered other valuable insights as you watched the video. We invite you to discuss these with a colleague. Please make an illustration to solve each of the following two-story problems and write the corresponding division equation for each. How are the problems alike? How do they differ? What did you notice about how these problems are alike and how they differ? What is the role of the divisor in each case? That is, what is its contextual meaning? What is the meaning of the quotient for each? You may have observed that the two problems are alike in that they both call for the division of 12 cookies and can be expressed as 12 divided by 4 equals 3. The key difference is what both the divisor and quotient represent in each problem. In the first problem, Talisha is putting 4 cookies in each baggie. So this splits the cookies into groups of 4. This means that 4 is the divisor, since it represents the size of each group. The unknown in this case, the quotient, is how many groups or baggies of cookies Talisha will be able to make. She will make 3 groups with 4 cookies in each, so she needs 3 baggies. In the second problem, the divisor, 4, represents the number of guests. Since there are 4 guests, Talisha needs to split the cookies into 4 equal groups. The unknown in this case, the quotient, represents the size of each group, or how many cookies each guest will get. With 12 cookies, shared equally among the 4 guests, each guest will get 3 cookies. This understanding of the meaning of the divisor and the meaning of the quotient in a division problem is key to making sense of division with whole numbers, and later with fractions and decimal numbers.
How do students in grades 3 through 5 use number lines as tools? Grade 3 students develop meaning of numerators and denominators, locate fractions on the number line, and reason about their relative sizes. In grade 3, students work with whole numbers on number lines. They order whole numbers and represent addition and subtraction problems on number lines. Third grade students use their basic understanding of fractions to estimate locations of familiar fractions on the number line, reasoning, for example, that 1/4 is half of 1/2. Grade 4 students rename fractions as equivalent fractions, locate fractions and decimal fractions on the number line, use estimation and equivalency to reason about relative sizes. Fourth graders make use of knowledge of equivalence for fractions, which enables them to locate fractions more accurately on the number line. For example, by recognizing that 1/2 is equal to 3/6, students can locate sixths with fair accuracy. Grade 5 students apply and extend previous understandings of multiplication and division to represent problem situations for fraction multiplication and division situations on the number line. In 5th grade, students solve multiplication and division problems on the number line, an extension of previous work with whole numbers. In earlier grades, students illustrated 3 times 5 as 3 equal jumps of 5 units on the number line, so that 3 times 5 equals 15. They apply this strategy to show 3 times 2/5 as 3 equal jumps of the distance 2/5 on the number line, so 3 times 2/5 equals 6/5, or 1 1/5. How do students in grades 3 through 5 make sense of operations with fractions and decimals? Making sense of operations with fractions and decimals requires that students estimate strategically, apply and critique reasoning, and connect important concepts such as place value and the meaning of each arithmetic operation. Students need to have developed a robust understanding of operations with whole numbers in order to build from that foundation to make sense of fraction and decimal operations. Grade 3 students illustrate and solve problems involving measurement, develop understanding of 1/2 through multiple experiences, reason about fractional values in comparison to 0, 1/2, and 1/2. In grade 4, students express fractions as the sum of unit fractions. They use concrete tools, diagrams, and number lines to strengthen understanding of fraction equivalence and multiplication of fractions by whole numbers. Grade 5 students use understanding of division of whole numbers to make sense of dividing a whole number by a unit fraction, such as 8 divided by 1/2, or dividing a unit fraction by a whole number, such as 1/2 divided by 8. They illustrate problems in story contexts, operate with decimal numbers to hundredths using various strategies, and explain and relate these to written methods. Number lines as tools for making sense of operations with fractions. This task, cross-country training from illustrative mathematics, will give you the opportunity to use a number line to solve a problem. Note how illustrating the problem on a number line supports students in making sense of multiplication of fractions. Respond to the 3 questions in cross-country training, including a diagram or number line and an equation for each problem. When you are finished, consider how the reasoning needed here builds on prior knowledge of multiplication for whole numbers. Nero ran 1 1/2 miles one day. Lily ran 3 times as far as Nero. How far did Lily run? One way to illustrate the action of this problem on the number line is to take 3 jumps of Nero's distance of 1½ miles to find how far Lily ran. After 1 jump, she has run 1½ miles. After 2 jumps, she has run 3 miles. And after the 3rd jump, Lily has run a total of 4½ miles. Jorge ran 3/4 times as far as Nero. How far did Jorge run? Nero ran 1½ miles, as shown in the upper image. Because Jorge ran 3/4 of Nero's distance, we use vertical lines to partition Nero's distance into 4 equal pieces. 3 of these fourths will represent the distance Jorge ran. Notice the location of the 1-mile mark for each runner. The vertical lines show us that Jorge's distance is a bit more than 1 mile. But how much more than a mile exactly? To determine the exact distance, we divide the whole 1½ mile distance into smaller pieces equal in size to the distance Jorge ran beyond the 1-mile marker. This allows us to see that 1 mile is comprised of 8 of these small pieces, and thus Jorge ran 9/8 miles for a total distance of 1½ miles. A common approach to this problem recognizes that Jorge's distance can be calculated as 3/4 times 1½ miles. A way to connect this calculation to a visual approach utilizes the same partitioning of Nero's distance into 4 equal parts as we have seen previously. 3 of these fourths will represent the distance Jorge ran. We need to determine what distance each fourth represents. We can do this using a calculation method. 1/4 times 1½ is equal to 1/4 times 3/2, which equals 3/8. So, if 1/4 of Nero's distance is 3/8 miles, then 3/4 of Nero's distance equals 3 times 3/8, which equals 9/8 or 1½ miles. Belinda ran 2 1/3 times as far as Nero. How far did Belinda run? Belinda ran 2 1/3 times as far as Nero, so 2 1/3 copies of Nero's distance will be equal to Belinda's distance. Let's build these copies in 2 stages. In the first stage, we see that 2 times Nero's distance equals 3 miles. In the second stage, we will determine Belinda's remaining distance. Belinda ran another 1/3 of Nero's distance. By partitioning Nero's distance of 1½ miles into 3 equal parts, we see that 1/3 of 1½ miles is 1/2 mile. This shows us that Belinda's distance was 3 miles plus 1/2 mile for a total of 3½ miles. In order to connect to prior knowledge, a teacher will often encourage students to replace fractions with whole numbers to determine how to proceed. For example, a student could substitute 2 miles for Nero's distance and solve the problem more readily, which also increases accessibility to the original problem. You likely noticed that in each case, the illustration typically shows 3 jumps or increments of the distance. By using the same structure they used for whole number multiplication, students can make connections between whole number and fraction operations. The visual approach just shown matches neatly to a symbolic calculation method using the distributive property of multiplication over addition. To use the U.S. standard algorithm for multiplication of fractions, we rewrite the previous equation using fraction form rather than mixed numbers. While algorithms are not the initial focus in grades 3 through 5, they can become useful when the numbers are less friendly. To recap, we have seen that students in grades 3 through 5 extend their flexibility with number, understand the operations of multiplication and division, use number lines as tools, and make sense of operations with fractions and decimals. It is essential that young learners have ample opportunities to use strategies, tools, and visual methods to make sense of these important number sense elements. Such experiences prepare students to apply formal algorithms with understanding as they move forward in their academic work.
So we've just spent some time thinking about the mathematics in the framework, particularly the number sense chapter. In addition to mathematics, we also want to consider how we are integrating social-emotional learning principles into our mathematics instruction. Consider the question above and jot down a few of your thoughts. Self-awareness, social awareness, and relationship skills are some of the areas that can be developed in students as they engage in mathematics. Some students may need more support and encouragement to discuss their thinking publicly. However, with continued intentional experiences integrated into our learning environments, students will continue to increase their social-emotional competencies and therefore increase their sense of agency. Let's dig a little deeper into the big ideas of social-emotional learning and some specific connections to number sense. The Collaborative for Academic and Social-Emotional Learning, or CASEL, has identified 5 core competencies of social-emotional learning. Those competencies include self-awareness, self-management, social awareness, relationship skills, and responsible decision-making. Supporting students' social and emotional development does not need to happen in isolation or as a separate set of lessons. It is possible to integrate skill instruction and practices that supports SEL development within the context of your academic curriculum. Let's dig a little deeper into what that might look like for each of the 5 SEL core competencies. Self-awareness is the ability to understand one's own emotions, thoughts, and values, and how those impact how you behave. When participating in activities that focus on the use of manipulatives and visual approaches, we are supporting the development of self-awareness by helping students learn to consider available resources and approaches and how they might use those resources to deepen their own understanding, identify their feelings about the mathematics task and solving problems using multiple approaches and strategies, identify their individual strengths and challenges, and have a growth mindset. Self-management is the ability to manage one's emotions, thoughts, and behaviors effectively in different situations and to achieve goals and aspirations. When participating in activities that focus on the use of manipulatives and visual approaches, we are supporting the development of self-management by providing opportunities for students to learn how to think metacognitively about the connections and relationships they are making in their thinking, make sense of problems and available tools and approaches before jumping into a solution, set personal goals and monitor and evaluate their progress during and after a problem-solving experience, utilize strategies to persevere when solving challenging problems and identifying relationships and connections between ideas, and communicate and justify thinking to the group while honoring the thoughts and ideas of others. Responsible decision-making is the ability to make caring and constructive choices about personal behavior and social interactions across a variety of situations. When participating in activities that focus on the use of manipulatives and visual approaches, We support the development of responsible decision-making by allowing students the opportunity to identify multiple approaches to problems and the connections and relationships between those approaches, learn how to use information to make decisions or choose appropriate strategies, anticipate the consequences of one's actions and choose appropriate actions, and reflect upon and choose appropriate ways to contribute to the learning community. Social awareness is the ability to understand the perspectives of and empathize with others, including those from diverse backgrounds, cultures, and contexts. The use of visual approaches and manipulatives in a cooperative learning setting, such as working in pairs or small groups, allows students to develop their social awareness. As they work in small groups using visual approaches and manipulatives, students can express their mathematics understanding while simultaneously understanding the approaches and mathematical arguments of their peers, recognizing strengths in others' problem-solving approaches, demonstrating perspective-taking, empathy, and compassion when working with others, and showing care for how others are feeling as they tackle math tasks. Relationship skills are the abilities to establish and maintain healthy and supportive relationships and to effectively navigate settings with diverse individuals and groups. The use of visual approaches and manipulatives in a cooperative learning setting allows students to develop their relationship skills. As they work in small groups using visual tools, students can express their mathematics understanding while at the same time sharing ideas and listening to other perspectives. Actively listening to the thinking of others, deciding whether their ideas make sense, asking useful questions to clarify thinking, and strengthening connections between ideas. Communicating effectively and attending to precision in sharing thinking and reasoning. Seeking to understand the perspective of others and resolving conflicts constructively, and offering support to their peers when needed. Number talks in particular can contribute greatly to these aspects of students' social awareness and relationship skills as they listen to and respond to their peers' thinking. More information about number talks is in part 1 of this module. These are just some of the ways the SEL competencies can be developed while we are supporting our students' mathematical agency. We know you will have other ideas to extend those lists as you integrate SEL into your math instruction.